Okay, we want to answer some questions just about 2 by 2 matrices, because we can generalize the results we get for 2 by 2 matrices into higher dimensions, and our procedures are very similar. Question, do eigenvectors always exist? Okay, well, it's going to turn out they don't always exist. We'll prove that. And we prove that just by considering a general matrix A. Well, actually this isn't a general matrix, this is a matrix with, it's a symmetric matrix. Okay, but do eigenvectors always exist? Okay, if they do exist, the answer is no, but if they do, they tend to come in pairs. If they do exist, how do we represent a vector or given matrix relative to an eigenvector basis? Okay, or given transformation, define a transformation by a matrix. What's the matrix that represents the transformation relative to the eigenvector basis? And it turns out that to do this, we use the matrix with eigenvectors as columns. And there's a very simple reason, which we've already seen, why this works. This is the P matrix. And we get a similarity transformation of the form PA, P inverse, where A is not necessarily the matrix with respect to the standard basis, but this is the general form of a similarity transformation. And we will use one of these transformations to go from one matrix to another, one representation to another of the transformation, and the other matrix to go from that representation back to the original. Okay, so really those are the questions we want, and we want to note that the matrix relative to the eigenvector basis is diagonal with eigenvalues on the diagonal. Okay, these are very important properties. That's a summary of what we're going to see, what we've actually already seen, but we're trying to kind of summarize things into a nice, neat package for the exam.